Hey everyone, and welcome to video number 18 in the series. Before we broach a new topic, I just want to mention something that we did in the previous lecture so that there will be complete continuity to what we did in lecture 17 and what we're doing in this video right now. And here's the result. We had a congruence, mod n, common factor of C on both sides, and we discussed when it was that we could, with absolute certainty, cancel the common factor of C on both sides and end up with a congruence that was true. When can we cancel this common factor of C on both sides and still maintain the sense of the original congruence? And we said that under these conditions, when the greatest common divisor of C and N is 1, then we can cancel. And that's synonymous with saying that C and N are relatively prime. C, N, relatively prime, which is also synonymous with saying that C is not a zero divisor of N, and C contains no zero divisors as factors. Okay. So that's when we can cancel and still have a congruence mod n. There's another way that we can cancel, and we will get a different congruence, but the integrity of the congruence will be preserved when we do cancel. And I'm going to show that to you right now. Okay, let's take a look at this example. Mod 5. And notice what we have here. This is 3 times 5, congruent to 7 times 5. And let me rewrite that so that the 5 is out front. 5 times 3, congruent to 5 times 7, mod 5. And here's our C. And here's our N. And you know what? I don't like that. Hold the phone. Okay, please forgive me. This is more what I had in mind. 15 congruent to 35, mod 10. And 15 and 35 have a common factor, 5. So 5 is going to be our C. And it turns out that C and N are not relatively prime. As a matter of fact, C is a zero divisor of 10. So we can't just cancel the 5s from both sides. We can't cancel C from both sides. However, here's what we can do. We can look at the greatest common divisor of C and N that's the greatest common divisor of 5 and 10, which is 2. And here's what the theorem says that we can do. We can cancel the C's and we will have a congruence that is true if we do mod n over C. That's mod 10 over 5. And 10 over 5 is 2. We cancel these things and we have 3 is congruent to 7 mod 2. And that's true. 3 is congruent to 1 mod 2. 7 is congruent to 1 mod 2. So this is true. Now let's look at another example that's not quite so trivial. It's not overly complicated, but it's not quite so trivial. Okay, this is not quite as trivial. 24 is congruent to 108 mod 21. Now let's see, is that true? 24 divided by 21 is 1 remainder 3. So 24 is congruent to 3 mod 21. 108 divided by 21 is 5 remainder 3. 5 times 21 is 105. We get a remainder of 3. So yeah, this is true. 24 and 108 are both congruent to 3 mod 21. So they're both congruent to each other, mod 21. And interestingly enough, all of these things have a factor of 3. Ooh, 3 times what? 36? Times 7. So our theorem says essentially that we can just cancel the common factor. And I should note, greatest common divisor of 24, greatest common divisor of C and N here's C and here's N. Greatest common divisor of C and N is 3. And so that means whoops. cancel the common factors. What's left is congruent mod n over 3. And that is to say 8 is congruent to 36 mod 7. Now, is that true? 8 mod 7 is 1. 36 mod 7 is 1. So yes, it is indeed true. Now, why do we care? Well, in a situation like this, we really don't care. Because this is a congruence that doesn't contain any variables. But if we have a congruence that does contain a variable or more than one variable, we want to know if we can cancel or not, just so that we can find the solutions to the original congruence. And that may involve applying this technique where we cancel out the common factors and we get a congruence of two things, mod n over c, and take that solution and work backwards to get all possible solutions of the original congruence. That's why we're interested in this sort of thing. Here's a good example to start off with. Find all solutions to the congruence 6x congruent to 3 mod 9. And again, we notice that all of the coefficients have a factor in common with n here. So let's write this as for what it is. And here's our C. Okay. Greatest common divisor of C and N is greatest common divisor of 3 and 9, which is 3. So this is our D, our greatest common divisor. So what we can do is say that 3 times 2x is congruent to 3 times 1 mod 9 and I'm going to put over 3. Because here's what we're going to do. We're going to cancel out the C's. And this is going to be congruent mod n over C. Now this is pretty easy to solve. Mod 3, there are only 3 values that we can plug in. We can plug in 0, that's not going to work. We can plug in 1, and we'll get 2 mod 3, that's not going to work. Or we can plug in 2, and we're going to get 4, which is 1 mod Okay. Now what we want to do is take this and first of all recognize that this is also a solution to the original congruence. So the solution that we got by simplifying the congruence is also a solution of the original congruence. And let's see how we go about finding those. Okay, now let's see where this puts us. We have a theorem here. If x naught is a solution of the congruence ax is congruent to b mod n, then all other solutions are of the form x equals x naught plus in over d, where d is the greatest common divisor of a and n, and I goes from 0 to d minus 1. Let's notice something here. If I is 0, that makes this term 0, so x equal x naught is a solution. And if I were allowed to go all the way to d, that would give us x naught plus I. Okay. Or rather, x naught plus n. But let's see, x naught and x naught plus n differ by n, so they're congruent mod n. If I were allowed to go all the way to d, then we would have d times n over d, which is n, and we'd have x equals x naught plus n. But we already have x equals x naught as a solution. If we allow x equal x naught plus n as a solution, and let me just write that down, x equal x naught, x equal, tell you what, x naught plus n, x equal x naught. What's the difference of these two solutions? N, which means that modulo n, these two things are exactly the same. So that's why up here, I has to stop at d minus 1. If I assumes the value of d and beyond, then we're just generating duplicate solutions modulo n. I equals 0 to d minus 1 generate distinct solutions modulo n. If we allow I to equal d and anything greater, that's when we start generating duplicate solutions modulo n. So allowing I to range from 0 to d minus 1 will guarantee that all of the solutions that we get with this formula are distinct solutions modulo n. Now, let's apply this to our example. Recall where we just were. We had a formula for generating all distinct solutions modulo n for this congruence. And we're applying it to this problem, or this exercise, where x equal 2 is a particular solution of the congruence 6x is congruent to 3 mod 9. D is the greatest common divisor of A and N. That's the greatest common divisor of 6 and 9, which is 3. Okay. And all other solutions are of this form. X naught plus IN over D. And that's X naught is 2 plus I times N, which is 9, over D, which is 3. 2 plus I times 3, or let's just say 3I, for I equal 0, 1, 2, and I stop at 2 because this is D minus 1. I equals 0. X is equal to 2 plus 3 times 0, which is 2. I equal 1. X is equal to 2 plus 3 times 1, which is 5. I equal 2. X equals 2 plus 3 times 2, which equals 8. And those are all of the solutions that we have. Anything else, any further values of I, will generate duplicate solutions. For example, if we let I equal 3, that would be 2 plus 3 times 3 is 11. But mod 9, 11 is equal to 2, or congruent to 2. Duplicate solution. So these are all of the distinct solutions mod 9. Now let's just make sure that these work. Let's just keep ourselves honest. X equal 2. Six times 2 equals 12, which is congruent to 3 mod 9. Check. X equal 5. 6 times 5 is equal to 30. And let's see. Divide 30 by 9, we get 3 with a 3 times 9 is 27 plus 3. So that's 3 mod 9. X equal 8. 6 times 8, 48. And if we divide 48 by 9, we get 5 times 9 is 45 plus a remainder of 3. Check. Okay. Well, that is our first example. Let's do a few more applying this same technique, okay? Please forgive me. Apparently I had this on when it should have been off and off when it should have been on. So hopefully we didn't miss anything. Find all solutions to 42x congruent to 12 mod 18. Here is our C. Here is our B, but that doesn't really matter. And here is N. Greatest common divisor of C and N. By the way, this does actually matter. I'll remind us why in a second. Greatest common divisor of C and N is greatest common divisor of 42 and 18. Let's see, 42 is 6 times 7, and 18 is 6 times 3, so that's 6. Now it makes sense. Oh, by the way, since the greatest common divisor of C and N divides B, solutions exist. Greatest common divisor of C and N is 6. 6 divides B, so solutions do exist. Now let's write this out in terms of C, in terms of D. In the last example, I'm not really sure if I drove that home or not. But the greatest common divisor of C and N divides B, we're in business. If greatest common divisor of C and N doesn't divide B, we need look no further. Now we'll just write this in terms of D. 6 times 7x congruent to 6 times 2 mod 18 here's our D, D. We can cancel the greatest common divisor and we're left with the congruence. 7x is congruent to 2 mod 3. And this is, let me write that a little bit more neatly. This will be pretty easy to solve because x can only assume 3 different values mod 3. X equals 0, we have 0 congruent to 2 mod 3. Nope. X equal 1, we have 7, which is congruent to 1 mod 3, not 2. X equal 2, we get 14. 14 is congruent to 2 mod 3. So x is our solution. X equal 2. Now we're going to find the general solution. Okay. X not equal 2 is not only a solution to the reduced congruence, but it's a solution to the original congruence as well. All other solutions All other solutions are of this form: x equals x naught plus I n over d, where I equals 0, 1, 2, d minus 1. So x equals 2 plus I times n, which is 9. No, it isn't. I equals n, which is 18. And d, greatest common divisor, that was 6, wasn't it? Okay. X is congruent to 2 plus 3i for I equal 0, 1, 2, 3, 4, 5. D is 6. This is d minus 1. Holy moly. We've got a lot of solutions. X equals 0. Sorry. Tell you what, let's do it over here. I equals 0. X equals 2 plus 3 times 0 is 2. I equal 1. X equals 2 plus 3 times 1, which is 5. I equal 2. X equals 2 plus 3 times 2, which is 8. I equals 3. X equals 2 plus 3 times 3, which is 11. I equals 4. X equals 2 plus 3 times 4, which is 14. I equals 5. X equals 2 plus 3 times 5, which is 17. Okay. Now, just to keep ourselves honest, we'll check them. Now, let's put this baby to rest. X equal 2. We have 42 times 2, congruent, question mark, 12 mod 18. Let's see. 42 times 2 is 84. 84 divided by 18, let's see. 4 times 18 is 72. With a remainder of 12, yep, that works. Okay. X equals 5. Congruent to 12 mod 18. Holy moly. Let's see, what is 42 times 5? 210 divided by 18. Yep. 18 goes into 42 times 5, 11 times with a remainder of 12. Okay, x equal 8. 42 times 8 is congruent to 12 mod 18. Holy moly, is this going to work? Let's see. 42 times 8. Let's see, that's 320 plus 16, 336. and we divide 336 by 18. Let's see. Boy, if you don't see this, oh, yeah, wait a minute. What, 8 times 18? I'm thinking. 8 times 8 is 64. 8 times 1 is 80 plus 6, 144. Remainder of 12. Okay, so that works. You know what? These numbers are getting so big, I don't think I'm going to check the rest of them out. But the first 3 checked out just fine. If you want to use a calculator, you can confirm the rest of these rather painlessly. I bet you thought I was going to ring the bell and it was going to be time for us to go out to recess, but no, we're not going to get to go out to recess just yet. We've been doing linear equations of this form. We got one more thing to do in this lecture, and there's an interesting comparison between what we are about to do and systems of equations, n variables and n unknowns. We're going to be solving systems of 2 equations and 2 unknowns, and there is a very strong analogy to be made between that and systems of equations, 2 variables, 2 equations. Just a reference here back to linear algebra. We have a system of 2 equations with 2 variables, x and y. And this system of equations can be expressed in matrix form this way. Let's see if I can still do this. ax plus by equals e. Cx plus dy equals f. Okay, I still got it. So we can take this system of equations and rewrite it in matrix form. And here's the kicker. This system has a unique solution exactly when the determinant of A, the coefficient matrix, is not 0. Now, what is the determinant of A? AD, CB or BC. We take the product going down, AD, and subtract the product going up, BC. This system of equations has a unique solution exactly when the determinant of A is not 0. In other words, when AD minus BC is not 0. Now, what in the world does that have to do with congruences? Here's an analogous theorem regarding a system of congruences. AX plus BY congruent to R mod n. CX plus DY congruent to S mod n has a unique solution exactly when this thing, do we remember that? This is the determinant of our coefficient matrix. This system has a unique solution exactly when the determinant of A and n is equal to 1, or when these 2 things are relatively prime. Now, there's some subtle things here. We're doing modulo arithmetic, right? Arithmetic modulo n. There is no such thing as modulo 1. If we're doing modulo n, n is 2 or greater. N is a natural number greater than, not equal to 1. So, in order for this thing to be equal to 1, this cannot be equal to 0. If n is a non-zero number, what's the greatest common divisor of 0 and n? It's n, isn't it? So if this thing is 0, then, whoops, I left something out. Son of a gun. Please forgive me. There we go. Our system has a unique solution exactly when the greatest common divisor of these two things is equal to 1. Now, if the determinant of A is equal to 0, all bets are off because the greatest common divisor of 0 and n is n. It's not 1. And we can't say, oh, well, what happens if n is equal to 1? No, in modulo arithmetic, there is no such thing as some integer modulo 1. Doesn't happen. So the only way, considering the fact that n has to be at least as big as 2, the only way that the greatest common divisor of this thing and this thing can equal 1 is if this thing is not 0. So that's an important observation right there. So this thing is not equal to 0. The determinant of A is not equal to 0, which is exactly what happens if we're solving for a system of equations and we want a unique solution. The determinant of the coefficient matrix A has got to be 1. It can't be 0. If we have a system of equations and the determinant of the coefficient matrix is 0, we ain't got a unique solution. We either have infinitely many or we don't have any at all. Now we might add, well, why do we need this at all? Why can't we just do this like we did with a system of equations? And here's the catch. If we were looking at a system of equations, and this was equal and equal, we'd get solutions if the determinant is not, as long as the determinant is not 0. But the solutions probably wouldn't be whole numbers. Since we're doing congruences and that involves modulo arithmetic, we only allow whole number solutions. And so that's essentially why we have to have this requirement that not only is the determinant of A not 0, but that these two things have to be relatively prime. Okay, here's our system of equations, and we're assuming that it meets the requirements, namely that the determinant AD minus BC is not equal to 1. I'm sorry, it's not equal to 0. And that okay, let's just say that we're given that this is 1. What do we do? Multiply congruence 1 by D multiply congruence 2 by B. And what do we get? Holy moly. We get dAx plus dBy is congruent to dr mod n. And we get bcx plus bdy is congruent to bs mod n. And we subtract. So let's see. This is dA, I'll write it as AD minus BC x. And what do we have here? dBy, or this is dB, but I could write it as BD. BDY minus BDY is 0. Okay. And then we have dr minus bs mod n. Oh, and guess what we're going to do next? Divide by AD minus BC. Ah, no wonder this thing can't be 0. And that will give us x is congruent to dr minus bs over AD minus BC mod n. Etc. Okay. Enough preliminaries. Let's actually work one of these babies. Well, this looks like a nice one. 4x plus 3y is congruent to 8 mod 12. 3x plus 5y is congruent to 6 mod 12. So what are our main characters? This is n. Okay. A, B, C, and D. And what do we need to make sure of? We need greatest common divisor of AD minus BC and n is equal to 1. I sure hope that happens. That's equal to the greatest common divisor. 4 times 5 is 20. 3 times 3 is 9. Oh, n is what? 12? And that's true. Greatest common divisor of 11 and 12 is equal to 1, thank God. So this has a solution, a unique solution. Okay, let's get on with it. That we have a unique solution. What do we do? Multiply congruence 1 by D congruence 2 by B. Okay. So that, let's see, D is 5. 5 times 4x plus 3y is congruent to 5 times 8 mod 12. Multiply congruence 2 by B. B is 3. 3 times 3x plus 5y is congruent to 3 times 6 mod 12. And let me make sure I did that right. 5 times 4x plus 3y. And B is 3c. Okay. I think we're good. And what does that give us? 20x plus 15y is congruent to 40 mod 12. And 9x plus 15y is congruent to 18 mod 12. Okay. And we subtract. And that will give us 11x is congruent to 20. Wow, this is too easy. Congruent to 22 mod 12. Okay. Now let me put the brakes on for a minute so I can clear off the board. Okay. This is what we have. We're going to solve for x. And there are a couple of ways that we can go about doing this in this particular case. We have 11x is congruent to 22 mod 12. And that's essentially the same as 11x congruent to 11 times 2 mod 12. And we're wondering, can we divide both sides by 11? It seems like we should. This would be the same thing as 11x minus 11 times 2 congruent to 0 mod 12. And this would be n. This would be our c. And greatest common divisor of c and n is equal to 1. So we can divide both sides by c. And that would give us x minus 2 congruent to 0 mod 12, etc. So the point is, we could divide by c, we can divide by 11 here, we can divide by 11 here. It's the same thing. And the fact that 11 and n are relatively prime means that we can divide and not compromise the sense of the congruence. So we're going to get x is congruent to 2 mod 12. Now just suppose that 11 and 12 hadn't been relatively prime. What could we have done? Let's just look at an alternative way of doing this. Let's see, what do we have? 11x congruent to 22. Mod 12, okay. And then I guess what I could do, I could subtract 12 22 and 10 are congruent mod 12. They differ by 12. And then I notice that 11 is just one short of 12. So 11 is negative 1 mod 12. So what I'm going to do is multiply both sides by negative 1. Whoops, negative 10. Now, negative 11 is congruent to 1 mod 12. Negative 10 is congruent to 2 mod 12. So, if these two things hadn't been relatively prime, I could have arrived at the solution this way also. So let's just note, we've solved for x. And let's just recall what our original system was. 4x plus 3y is congruent to 8 mod 12. And what was it? 3x plus 5y congruent to 6 mod 12, I think. Okay. We're guaranteed that we have a unique solution. And we know what x is. It's 2. We can use either of these equations to find y. So let's see. 4 times 2 plus 3y is congruent to 8 mod 12. That is 8 plus 3y is congruent to 8 mod 12. And we'll just subtract 8. 3y is congruent to 0. Mod 12. Okay. Hold on for a second. You know, I'm looking at this thing and it bothers me because what I want to do is divide both sides by 3 and say, aha, y is congruent to 0 mod 12. But 3 and 12 are not relatively prime. 3 is a 0 divisor of 12. So I can't divide both sides by 3 and be certain that I haven't compromised the original sense of the congruence. So this is inconclusive because 3 and 12 are not relatively prime. I can't just whimsically divide both sides by 3 and say y is congruent to 0. Well, this is what I got when I plugged in x equal 2 into the first congruence. If there's any justice in this world at all, the same thing is not going to happen when I plug into this congruence. So let's see. 3x plus 5y is congruent to 6 mod 12. And that means 6 plus 5y is congruent to 6 mod 12. And I'll subtract 6 from both sides. 5y is congruent to 0 mod 12. Okay. And here's the clincher. Greatest common divisor of 5 and 12 is equal to 1. 5 is not a 0 divisor of 12, so we can divide both sides by 5. Okay, so it did turn out to be y congruent to 0 after all, but down here we couldn't be sure. Okay, xy is equal to 2, 0, mod 12. Now, are we going to let it go at that? No, we're going to check. Okay, let's check. 4 times 2 plus 3 times 0, congruent to 8 mod 12, you bet. 3 times 2 plus 5 times 0, congruent to 6 mod 12, absolutely. Just a remark, this solution is unique mod 12. Are there other solutions? Yes, but they will be congruent to 2,0 mod 12. So if we're just looking for ordered pairs, xy, we use xy equal 2,0 as a particular solution. All all other solutions are going to be of the form xy equals 2, 0 plus some integer I times 12, some integer j times 12. So we can generate infinitely many solutions that are congruent to this mod 12. What makes this one special? This is the only one that has xy between 0 and 11. All of these other solutions are going to have either xy or both less than 0 or greater than 11. So as far as mod 12 goes, and when we think mod 12, we think 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is a unique solution. This is the only solution that has xy coordinates between 0 and 11 inclusive. There are infinitely many other solutions that are congruent to this, and they consist of this particular solution plus some multiple of 12 in the x coordinate, some multiple of 12 in the y